I'm Gary Kidney. I work in academic ITS, and I'm going to introduce three people to you who will be part of the next panel. This panel is an interestingly diverse panel. Come on through. You're going to hear from a grad student, a postdoc, and a professor. You're going to go from black holes in the center of galaxies to Australia's outback and to political behavior of America. So the first speaker will be Vivek Ashok. Vivek is here to my left. He is a PhD student in the Department of Political Science. His interests are political behavior, quant methods, and political economy. His research looks at the effects of information about income inequality in voter attitudes and behaviors. And in addition to that, he manages the ISPS Behavioral Research Lab. Sitting beside him now at the moment is Haynie. Haynie is substituting for Claire Bourne, who would have been our speaker today on Australian languages. Claire is unable to be here. Haynie is the postdoctorate associate of linguistics at Yale University. She's a specialist in historical linguistics and language documentation, particularly on the languages of Australia and some American Indian angles. Her work involves not only the linguistics, but also cross-cuts to anthropology and evolutionary theory. And I'll introduce our third speaker, who doesn't appear to be here yet, but we hope he comes popping in before his time to present comes up. Paolo Coppi is a professor of astronomy and physics. His main interest is in high-energy astrophysics, particularly what happens with gas and radiation physics near where black holes meet in the universe. In addition to that, he leads a project called Yale Quest in Chile that looks for non-stellar variable phenomena through the world. So first off, Vivek.
Good morning, everyone. Thank you so much for being here, and thank you for letting me present about what we've been up to at ISPS. So my name is Vivek Ashok. I'm the lab manager at the Institution for Social and Policy Studies Behavioral Research Lab. And over the past year, we've set up a behavioral research lab, and we are open for business now, and I wanted to talk to you a little bit about the lab, about behavioral science research in a laboratory setting. And so the brief overview of the talk is that I'm going to first talk a little bit about lab research in the social sciences. I'm going to talk about what we did at ISPS and what we're doing differently. I'm going to talk about the data gathering process, and I'm going to talk about what we're thinking about moving forward. So just like the sciences, social scientists have developed a number of theories over many, many years, and a number of these theories give rise to questions of cause and effect. So as a political scientist, I'm interested in why people vote. We have a theory that tells us that in closer elections, more people turn out, but in closer elections also see greater media coverage and more campaign activity. So how do we disaggregate the effects of each one of these things? And a good way to do it is in the lab, by performing an experiment. In more practical terms, governments and academics care about the effects of policies. So if we roll out a school voucher system, what is the effect of the voucher system on standardized test scores, let's say? So social scientists have been doing randomized experiments since the 1920s, and they're attractive because we have control over both the treatment and the assignment to treatment. More specifically, a lab experiment of the social sciences contains some common features. First, subjects are recruited and brought to a common space, a common physical location. They engage in behaviors that are recorded and are tracked, and they do so all under the direction of a researcher. So these are the common elements of a lab experiment. And they've been very commonly used by psychologists and behavioral economists in their research. The unique features of a lab compared to other contexts where we can do experiments are the following. So we can more precisely administer treatments. So when presenting a video, I know the quality of the video is going to be equal across all participants viewing it. We have control over outside influences. So I can control the level of interaction people have with each other while taking part in the study. And I'm able to collect a lot of data before and after the session, building a richer data set than average. And finally, sometimes we do want outside influences, and we want people to be able to collaborate and to compete with each other in the lab, and so we're able to assign them more complicated tasks and monitor their behavior. So what's different about the ISPS BRL? The first thing is that we're truly interdisciplinary. So we're allowing for research of many different types in the lab. We're equipped to deliver behavioral games using a software package called Z-Tree. We're able to deliver survey experiments with tighter control using Qualtrics or any other web-based platform. And we also have Media Lab, which allows us to deliver rich media, like very high-quality videos. And I think probably the most important thing about our interdisciplinary focus is that we're constantly evolving at the BRL. So as researchers approach us with new needs or new methodologies pop up, we are ready to incorporate them into what we can deliver. So how did we set up? We set up with the generous support and encouragement from a number of people, primarily the Institution for Social and Policy Studies, the Center for the Study of American Politics, and the Yale Law School. And specifically, we'd like to thank Jacob Hacker, Alan Gerber, Greg Huber, Robert Post, John Bullock, and Ernie Marinko. The first thing that we thought about was the space. So we needed a place where participants could enter the lab from the street with minimal disruption to anyone else in the building, and they could proceed conveniently to our lab space. The second requirement that we thought about was our technology. So we purchased 16 workstations and a server that can handle delivery of these 3 different types of experiments, primarily. And we worked with network operations to set up a network with the bandwidth and the reliability we needed to deliver rich media to the workstations. We worked with the Human Subject Committee for us to develop a participant pool to have people that are willing to be invited to take part in sessions, and also just maintenance of the lab. And finally, we worked with Treasury Services to develop a payment protocol where we can pay the participants that come into the lab in cash and then reconcile those with researcher accounts later. So what we had when we did all of this was a lab space. So this is our entrance between 87 and 89 Trumbull. I'm sure many of you have passed it, and if you see the sign hanging, it probably means we have a session in progress. And then the space itself. So this is the lab. In setting this up, there were challenges, however. And I think what our greatest challenge is control. So the advantage of a lab, as I said before, is that the researcher can control almost every element of the participant experience while they're in the lab. But what that means is there needs to be control over the workstations, and there needs to be a lot of uniformity between the environments that participants are experiencing when they're in the lab. So we had to control people's access to programs, to drives, make sure that a participant couldn't plug in a USB flash drive and copy data, along with websites and other system settings. And the way we attempted to do this was by using local policies in Windows. But they were pretty ineffective. The first thing is there are hundreds of selections that you need to make, and once you change one on a workstation, you have to go to every workstation after and make that same change. And so it was very ineffective. And so ITS Endpoint Engineering really came to the rescue on this. And we added the workstations to the Yale domain and then created different user accounts for each type of study. And now what we're able to do is we merge these local policies into a group policy, and all the accounts are managed centrally on the server. And so if I make one change or allow new access to one part of the computer or a new website, that's reflected across all of the workstations. So while we did most of this in-house and wanted to have a lot of control over the way we saw this lab developing, we did run into some obstacles, and ITS really helped us out. So now we have the lab. How do we gather data? We gather data both in and outside the lab. We gather data at 3 specific points. The first point is at registration, the second is in the lab itself, and the third is any after-session data that we might choose to gather. And all of this data can be merged into one data set. So upon recruitment, and we've been doing this since spring, where we've been reaching out to Yale students and staff to join our participant pool, when they register, they're assigned a user ID and an account, and asked to take a pre-survey of about 30 questions. And this pre-survey asks questions about demographics, the background, some political attitudes, some personality traits. And this is managed by a cloud-based tool developed by Sona Systems. And what's very nice about this tool is that we are then able to create researcher accounts for the researchers that will be using the lab. And what happens on this cloud site is that participant data is updated in real time, and researchers have access to it immediately while protecting the confidentiality of the participants. So participant data is updated, and then researchers can invite them to take part in studies that they would like to field in the lab. And based on these 30 different criteria, they can get the sample that they want. And they can invite them directly, and all that communication happens through the Sona Systems website and is monitored by administrators in the lab. And finally, so this data is not only interactive to the researcher, but is also downloadable as a data set. The second point of data collection, of course, is in the lab itself. So during a session, we collect data on all the behaviors that participants undergo, and we also compensate participants about $15 an hour for their time. That's what we're asking researchers to compensate participants. And depending on the type of activity, there might be financial incentives as well. And so participant behaviors, as well as their payment and attendance, is recorded. And throughout the sessions, participants are only identified by this user ID that's generated upon registration. And at the end of the session, now we have data on attendance, your behaviors, and your payment. And so what this allows us to do at the end of a session is build one big data set of the pre-survey and the session. And we also document the protocol itself, the experiment itself that's delivered, where the randomizations take place, so on and so forth. And we reconcile the cash payments that we advanced from the Treasury Service with the researcher accounts. We update the participant profiles online with their attendance information. So future researchers who may wish to disqualify participants that took part in a certain type of study can do so. And depending on the discipline of the researcher, they may get pushback from reviewers at certain journals about how representative their sample is. And so we have a way of directing researchers to outside sampling firms to replicate their protocol. So moving forward, what are we thinking about? Right now, we are mostly spending our time on recruitment. We would love to get as many students and staff members as possible in our pool. We're inside Yale at the moment, but are certainly thinking about recruiting subjects from outside the Yale community. While at the moment it's pretty streamlined for a participant, we're thinking about a way of gathering all the materials that a researcher would need to be acquainted with the lab, the things that we are able to offer and put it in one place. So part of the website that we have at the BRL should be dedicated for researcher use. That's something that we're developing. And something that we've been thinking a lot about is how to archive protocols, not just data and the programs people write to analyze data, but what is the best way to archive an experimental protocol, especially when some of these files are very specific to programs that might not be in existence 20 years from now. And we would like researchers to be able to find a protocol and run it, even if the original program used to deliver the experiment is no longer available. And I'm sure we're missing things, so I would love to hear from the audience about what your thoughts are about the lab, what we could be doing differently, and what you would like to see us do in the future. Thank you, and please sign up.
All right. So I'm going to take an entirely different tack here and talk a bit about how data has changed the field of linguistics in terms of the types of questions we can ask and answer. I'm going to be speaking in place of Claire Bourne, who's unable to be here today. But I'm talking about a joint project that we worked on together, so hopefully I'll be able to do her justice. So linguistics is a field that has always relied on data. It's a field based on empirical observations about how people use language, how languages change over time, and how languages are. So we use a lot of different types of data to understand speech, language, and the use of language. Everything from fine details of acoustic signals to broad corpora of actual spoken or written data. So data has been an important part of linguistics for a long time, but the scale of the data that we have available to us has been evolving, just as it has in many other fields. Linguistics is unique in that it cross-cuts a lot of other areas, including both humanities and social sciences. So we find interactions between linguistics and fields such as anthropology, and even harder sciences such as biology. So today I'm going to talk a little bit about a specific question that we've been able to get better traction on using a larger data set than has been available in the past. And specifically, I'm going to talk about sound symbolism in Australian languages. So what is sound symbolism and why do we care about it as linguists? Well, one of the fundamental ideas about language that can be traced back to Saussure in the early 20th century is that the relationship between sounds and the meanings they represent is an arbitrary one. So we as English speakers know this thing here in this picture as a horse. And there's nothing about an H or an O or an R or an S, those sounds, that has any relationship to this animal, right? They don't represent the sound it makes or the way it moves or the way it looks. And in fact, in other related languages like French and German, entirely different sounds are used to represent this thing. So there's really no relationship between the sounds that we use to represent this object and the object itself. But we know as linguists that there are places in language where that arbitrariness assumption gets violated. So there are places in language where the associations between meanings and the sounds that represent them are iconic in nature. So just for an example, we'll look at a different creature. And if we're speaking Northern Sierra Miwok, you would call this hekeke, which, if you know what a California quail sounds like, you might recognize that as something that resembles the call of this quail. So here we have a really non-arbitrary association between a thing and the sounds we use to represent it. We find this in English, too, with conventional patterns, like the use of gla the sound sequence GL, to mean something about luminosity. So we have words like glimmer and glisten and gleam. And if we had other words come into the language with this GL sequence, we might expect other words that come into the language to represent things about luminosity to also use this GL sequence. And finally, we have a more abstract type of symbolism that's been studied in linguistics, where higher acoustic frequency sounds are associated with meanings of smallness or nearness. So this is a rather abstract or synesthetic type of sound symbolism, where people use specific sounds and specifically capitalize on their acoustic properties to represent things about the real world. So an example is the word küçük in Turkish to mean small or little. And people have found examples of this in languages across the world. So there's a whole number of references listed here where people have looked at meanings that mean small or near or large and far, and have found that there's sort of a line where high acoustic frequency sounds are used to represent those things that mean small or near, and low acoustic frequency sounds are used to represent those things that mean far or large. But this is kind of a problem in that people have gone about finding data to discuss this problem by pulling out examples from languages sort of at random as they find them. So many of these resources that I've listed here, they provide cherry-picked examples of sound symbolic forms in many different languages. But one of the questions that's remained largely unanswered through these earlier methods where people have looked at small samples of cherry-picked data are why sound symbolism arises. So is it something that happens as an accident of history, where related languages just happen to inherit the same forms? And so we find the same sound meaning patterns occurring in multiple languages because they have inherited cognate forms. Or is it something cultural, where speakers learn to associate sounds with certain meanings, such as the English glimmer, gleam, GL means luminosity example? Or, in fact, is sound symbolism actually something more universal? So thinking about these magnitude-related sound symbolic categories, where acoustic frequency is correlated with size or distance, we need to ask, is this an accident of history? Is it something cultural, or is it something universal? And debate has centered around this question for magnitude-related symbolism, because when we have a small sample of forms, we can't really answer this very well. So today, I'm going to talk about some claims related to magnitude sound symbolism, and that is the old question. So the old question is, what causes magnitude sound symbolism to arise in many languages of the world? And the new question is, how does it emerge in Australian languages? What representations of magnitude sound symbolism do we find attested in Australia? So quickly, I'm going to take you through a little bit about the prior work, talk about the data we've used, and then talk about how our results suggest new conclusions about the nature of sound symbolism. So the data we have to work with for this particular study is quite different than what's been used before. Whereas earlier researchers looked through dictionaries or maybe word lists or just their own knowledge of, say, Indo-European languages, we've actually got a large data set available to us. So Dr. Bourne has collected a lexical database, a database of words from Australian languages that has nearly 800,000 items in it. For linguistics, this is big data, especially for an area like Australia, where the languages have not been well studied. So some of these languages have very minimal documentation. We're going to look at a sample of 104 Pama-Nyungan languages, that is 104 languages that belong to a large language family of Australia, and also 16 non-Pama-Nyungan languages, so 16 languages that belong to about 9 other families from the same geographic area. This is a type of sampling that wouldn't have been available to us earlier in the history of linguistics. And we're looking at languages for which we have large lexical samples, so languages for which we have more than 400 words available, which covers a good percentage of Australia. So when we look at our 120 language data set, we have good coverage over Australia, except where you see kind of the broad, empty western desert, where simply there isn't a lot of population. There's not not a lot of languages spoken there. So we've got an empty spot, but we have good coverage of the actual linguistic diversity of Australian languages. So for Australian languages, because no data set like this has ever existed before, we don't know a lot about symbolism. But we do know that in a handful of Australian languages, there's anecdotal reports of symbolism, for example, in things like onomatopoetic animal names and things like that. And there's one systematic study of sound symbolism, but there's nothing that compares across languages. So we don't know much about sound symbolism in Australia in general. And in the few cross-linguistic studies that do exist looking at sound symbolism, Australian languages are underrepresented. The data just simply has not been available before to look at symbolism in these languages. Now, Australian languages are an interesting case study to look at for sound symbolism because unlike the more familiar Indo-European languages, where some of these ideas about sound symbolism were first developed, or the North American languages, where further study of sound symbolism has occurred, Australian languages have unusually small vowel inventories. So if you look at this diagram, we find just 3 vowels that are typical of Australian languages, whereas they have large consonant inventories. So we might expect symbolism to be manifested differently in Australian languages than it is in other languages. So what we did was to compare sets of vocabulary that we expect to be associated with sound symbolic sounds. So things that express meanings of bigness or smallness or nearness or farness with the general vocabulary samples we have for each individual language. So we looked at lexical samples between 400 and 8,000 items for each of these languages and split it out into categories: general, distance, and size-related categories. And what we're able to do with this large data set is, instead of looking at individual forms in individual languages and using that as the entire basis for our understanding of sound symbolism in that language, we're able to pool language data and examine patterns across the languages of this region more generally. So we looked at percentages of vocabulary. Since we have word lists of different lengths, we don't want to throw away any data. So we looked at percentages of vocabulary that seem to show sound symbolic patterns. And we looked at relative frequencies of sounds within these samples of vocabulary items, so that we could see whether observed patterns match our expectations or differ from them. In the past, one of the big questions that's arisen that's been unanswerable about sound symbolism is when we find evidence, when we find attested examples of high-frequency sounds corresponding to smallness meanings or vice versa, low-frequency sounds and largeness meanings, do these things happen by accident? Is it just because these languages have these sounds, or these sounds are frequent in these languages, that we find these patterns? Or is it something about these words themselves or these meanings? So we're able to better answer that with our comparative process. And we're able to measure the contribution of relevant sounds to symbolic patterns in different ways. So we can look at the percentage of sounds in a sample that are of a particular type, or we can look at the percentage of words in a sample that contain a particular type of sound. So we're able to use a simple one-tailed paired t-test to compare our symbolic categories to our general vocabulary samples and answer the question of whether the frequency of sounds in magnitude-related vocabulary is higher than its frequency in the general vocabulary of the same language. So we did this for a number of different categories: overall kind of high acoustic frequency symbolism categories, overall low acoustic frequency symbolism categories, and then subsets of these symbolic word lists that represent meanings of size and meanings of distance. So just to give you a little sense of what we're looking at words like these for our magnitude-related vocabulary, words like low or shallow, words like far or deep, and also words like thin, wide, fat, large. So these are the meanings we're interested in looking at. So the results we found are interesting in that they support some of the ideas that have been proposed by earlier researchers, but they also open up new questions. So we were able to identify patterns relating palatal consonants, which are a particular type of consonants that are associated with high acoustic frequencies, with the kind of overall category of words that mean smallness or nearness, and also individually with those smallness and nearness categories. We found a very strong pattern here. But when we look at front vowels, which are a type of vowels, things like E, A, that are typically associated with that smallness or nearness sound symbolism, we find that they don't generally correspond with this high frequency category of symbolism. But within the nearness category, we find strong associations. So smallness doesn't necessarily seem to be associated with front vowels, as has been proposed by earlier research, but nearness does. And then when we look at high vowels, we find similar patterns where there's a less clear association overall between the sort of smallness, nearness, and high vowels. But when we look at smallness, high vowels seem to represent smallness in particular. So here we're able to get a finer grained understanding of what's going on with different types of sounds and different types of sound symbolism than was possible before. When we look at nearness, we also find an association between nearness and high vowels that's not quite as strong as what we found for front vowels. And then when we look at the opposite patterns, things are a little bit messier. So we found pretty good associations between the smallness and nearness meanings and some of the sounds that have been proposed to represent those types of meanings. But when we look at largeness or distance, we find that the patterns aren't quite so clear-cut. So we find relationships between velar consonants like k or g and meanings of distance, but we don't find very good associations between those same consonants and meanings of size. When we look at back vowels, which are another category of sounds that are supposed to be symbolic, so vowels like oo or o, we find kind of mixed results. We don't have a very clear-cut pattern for how these relate to distance and size meanings, whereas low vowels seem strongly associated with both distance and size meanings. So we've got complicated results happening here for distance and size. So looking at the results more generally, we find good support for this sort of high-class symbolism and more messy support for this low-class symbolism, but there's a stronger association between high-frequency sounds and smallness or nearness meanings than there is between low-frequency sounds and distance or size, large size meanings. We find better support for magnitude symbolism in consonants and distribution of consonants across words than we do with vowels, which is another interesting finding that's not been discussed before. And we can relate this to Australian languages and their relative phonological inventory sizes. So as we discussed before, Australian languages have relatively few vowels, but a lot of consonants. And so we can help to determine whether this is a function of inventory sizes or an independent fact. So we expected associations between these high-class sounds and front vowels and palatals and high meanings, and we found that. We also expected associations between these low-class sounds, so back vowels and velars, there's a typo, and low meanings. And we found symbolism in both meanings that are associated with size and with distance. So magnitude symbolism seems to be robust in both of these domains. But we found some unexpected things as well that earlier studies that were based on, again, these sort of cherry-picked examples from a small number of languages wouldn't have predicted. So we found that for Australian languages, consonants are more robustly associated with magnitude symbolism than vowels. And we also found that smallness seemed to be better supported, seemed to be associated with more symbolic sounds than largeness. So just looking at what's going on with sound symbolism more generally, here's where we have an opportunity to answer questions that weren't very answerable when we were just looking at small data sets. So for Australian languages, do these patterns of sound symbolism that we find across languages arise from some sort of universal tendency for people to express meanings of size or distance with certain sounds? Or does it arise for other reasons, like language-specific origins, where these languages just happened to have, by chance, developed words for these meanings that happen to include these sounds? Or could it be that these languages because many of them are related, have inherited the same words and sound symbolic patterns from a common ancestor? Or could it be, as we find in the Americas, that sound symbolic patterns have spread aerially from one language into neighboring languages and so on and so forth? We're able to gain traction on this with our large data set. So we're able to find that it's unlikely that this is a language-specific thing that just happens to co-occur at random in many languages of Australia. So we find very widespread patterns of sound meaning associations, and specifically we find symbolic associations between sounds and meanings in 54% of the languages in our studies. So using Fisher's exact test, we can compare the occurrence of sounds in magnitude and general samples for each individual language, and we find good evidence that most of the languages in our sample show sound symbolic patterns. There is some variation, though, in exactly which type of sounds get used to express these sort of symbolic meanings in these languages. So although most languages show some evidence of sound symbolism, they employ sounds differently in symbolizing meanings. So we can see that there's a widespread preference for using certain types of sounds for certain meanings, but there's a lot of local variation in how these things are manifested. This isn't necessarily a surprising finding, but it does help us to rule out language-specific origins for these things. We can also figure out whether there's evidence for sound symbolism being a genealogical process in these languages. So looking at Pama-Nyungan and non-Pama-Nyungan languages, that is, languages from these 10 different language families, we can demonstrate that sound symbolism shows up in languages across all of these language families. We also find that within different subgroups of the Pama-Nyungan family, we find significant sound meaning associations. And finally, when we run more sophisticated statistics on this data set, we can find out that there's very little phylogenetic signal in the sound symbolic patterns that we find. So using a measure of phylogenetic signal, Blomberg's K, we show that there's very little evidence that this is something that traces through the phylogenetic trees that relate these languages to one another. I'm going to skip a little bit through this aerial origins section. We tested for spatial autocorrelation in the data as well. Again, something we can do because of the data that we have and the coverage that we have of Australian languages. And we didn't find any specific spatial autocorrelation within this data set. So this leads us to believe that there's good evidence for sound symbolism in Australia. That we find some of the same patterns, especially in terms of the types of vowels that are used symbolically in these languages, as in elsewhere in the world. But we have a more complex pattern arising where we've got evidence for vowel height and vowel frontness to be involved, and the significant use of types of consonants that have never been reported to be associated with symbolism. So to sum up, we have support for this frequency code idea, this idea that there's a universal tendency for people to use acoustic frequency to encode information about size and distance. But we have a lot more information now about the language internal factors that help to determine how this sort of symbolism is implemented from language to language. Thank you. There are questions later, right?
I'm not sure.
It was Coppi. Okay. Maybe did it.
Right here?
Yep. Underneath that one.
Underneath that one? Okay. Let's close that. Move it out of the way. Yeah.
Yep. That's it.
Good.
Okay. Make it full page. Let's see.
Where is it? Where is it? I'm missing. Enter full screen. Oh, slideshow. Okay.
Okay, thank you. So I'm here, I guess, to tell you a little bit what's going on in astronomy and astrophysics and
astronomy is a branch of physics. Some people will disagree with that, but it has connections to that. And the talk will fall on a bit on the themes that came out last year, where there were talks by physicists and another astronomer, and also some people doing climate simulations. This is a big overlap. Okay, so this is the kind of stuff I do. This is our introductory slide when I show up and give a talk. The guys that started out being interested are these, which are supermassive black holes that you might think are strange systems. They have gravitational singularity. They eject matter at the speed of light with these jets. But through big data type things, in the sense of we develop surveys that can find more and more objects, we found that almost every big galaxy has a black hole at the center. All right? And moreover, if we take our galaxy as a black hole, and if we take the matter that fell into the black hole and we think we kind of understand what's going on, and compute how much energy was released by the matter as it fell in, it's a huge amount, and if we spread that energy all over the galaxy, our galaxy would be blown to bits to infinity. So these little black holes that turn out to be everywhere can dramatically disrupt and change the structure of the universe that we see. So as time has gone on, this used to be a kind of esoteric study for people who build atom bombs and stuff like that, because that's the kind of regime you're in. But now it's connected to other different kinds of astronomy. Okay. So first thing, in terms of computing and big data in astronomy, what often happened, the first real need of big data was in studying systems like this. The reason this kind of system is complex is in order to figure out what's going on, you're in a regime where you have gas and radiation going around, but the gas often has a low density. So that means two gas particles hitting each other. They're not really particles. They can go through each other. So at a given point in space, you can have photons and particles passing right through each other. So to understand what's happening, you need to understand how much stuff there is at every point in space. But not only that, you have to understand how much is moving in every particular direction with which velocity. So your problem is not a three-dimensional problem. Where is the stuff? It's also where is it moving and how's it moving. That's a six-dimensional problem. And as you quickly discover by looking at the universe, I'll show you in a second, the universe and astronomical objects are not steady in time, so you had to add the time dimension. So if you have, I don't know, you sample some dimension, like, okay, I'm going to study this system, and I'm going to take a box a meter in size and chop it into hundredths, okay, and I do that for all the other dimensions, my problem grows as a complexity of hundredths to the seventh power. You double the amount of resolution you have, your problem gets incredibly complex. So the reason why certain provosts and in general deans that recruit faculty in astronomy always groan when the astronomer walks into the room is, whatever you throw at it, I can suck up whatever computer power you need. And it's the same situation if you go to the climate studies people over here. If you do weather prediction, you need to have great control over the boundary conditions and lots of computers, the initial boundary conditions. So you need to sample, for example, the temperature of the Earth on meter squares. That's what we kind of do now, and then evolve it forward in time. And if you want to get to 10 predictions 10 days down the road, you need massive supercomputers. Someday we might want to go for hundreds of days or do global climate change. Our computers are not up to the task yet. We're getting there, and it's a miracle we managed to get where we are now. But that's why there's always, from the theory side, okay, try and understand climate, which is not astronomy, but the climate, the weather around here, there's an insatiable demand of computer power. All right? And why is it big data? Because you need the largest number of computers, clusters. These days you do things in parallel. And for example, a cluster at Yale has 10 terabytes of RAM. And so if I'm a simulator, I don't have access to the full cluster. But if I'm at supercomputing clusters, national supercomputing centers, I do. I'm going to be dumping out snapshots of what's happening around this black hole as often as I can. All right? Which means maybe you're going to let me have 100 snapshots. So 10 terabytes times 100 snapshots is 1 petabyte, which kind of counts as big data. So that's always been happening. The thing that's changed, and I'm actually here to talk about, is the other aspect connects to her talk. When people did astronomy, the stereotype was as a person climbing up on the mountaintop, looking through his telescope, freezing to death, and finding some really weird object that exploded. And as often the case in her case, that was a cherry-picked object. Okay? Because they were looking at one point in the sky, and we'll see about stars exploding later, and they just happened to see this one. And for the first, from 1950 to 1970, there were maybe sort of 100 supernovas known. A supernova is a star in a death row that explodes and makes a very violent explosion. And they're all over the universe, but you have no idea where to look, and they last for 10 days, and if you don't happen to be looking in the right direction, they're gone. Okay? And so people made up theories of supernovas. This is the archetypal supernova. This is what they all should look like. And everybody went to work explaining it. And then, as time has gone on, we now have samples of thousands of supernovas. And guess what? They all look different from the first one that was discovered. Okay? Maybe like the sounds, the frequencies are all wrong in her case. And maybe a better example is we look at our own solar system. At first, we thought we were unique. Then, from studying the motions of wandering objects in the sky, we discovered planets. All right, there are a few planets that are a bit different from us, but maybe everything else looked like us. And you open books, there's a nice theory for how the solar system formed. Then, now we found hundreds of solar systems, and most of them look nothing like ours. Okay? So we're learning something from a lot. So it's the stage where big data and technology allows you to expand the sample sizes where the big progress comes in. And to expand the sample sizes, where we're at these days in astronomy also is big data in the traditional sense of petabytes of data. So let me tell you a bit about that. Okay. And there's a project at Yale which kind of classifies as big data. I'm sorry, the quality is not quite so good. What happened was that in high energy physics, there's a person called Charlie Balte who worked in building physics, cutting-edge physics detectors. And one way that you measure how particles interact in a particle collider is you put a bunch of silicon strip detectors that basically capture the charge from when a fast particle comes in, and you collect it, and those are called charge-coupled devices. And at one point in his life, he got sick of particle physics because we've discovered everything that we can discover, kind of. So he went down a few floors and talked to the astronomers. You know, I know a lot about this CCD charge-coupled device. I know how to build lots of them. Can we do something with that? And yes. And so he put 112 of them in here and made a camera with like 161 megapixels. Okay? So that's still better than an iPhone, but maybe not for long. All right? And this camera, through various permutations, has ended up on an instrument called the Schmidt telescope, whose sole purpose is to take large pictures of the sky. So people have always known that they need to make large samples. So what did they do in the old days? Well, all we had was photographic plates. So people literally spent years photographing every single part of the sky. And so our previous knowledge came from photographic plates, but they're not very good compared to CCDs. So basically, this project replaced the photographic plate holder with a modern optical detector. And this, to get the project working, also not only do you have to retrofit the telescope, but you have to put in data links. There's about 100 gigabytes of data a night that has to get transferred from Chile, where this telescope is, up to Yale, and then some of it shipped off to Berkeley. And, let's see. Just to put it in perspective what this camera can do, though, this picture is more or less right. If you hold your thumb up, that's sort of called 1 square degree in the sky, and the moon gets blocked by that. This is kind of what the moon looks like on this camera with the sky projected on it. So this takes a picture of a relatively huge swath of sky. All right, not as big as you'd like, but it's a lot. And in one night you can cover approximately a 20th of the sky. So after a month you can have covered the whole sky, and then you start repeating it. Okay, so that's what we're at. Okay, and this shows you, slightly out of date, how much sky has been covered. In this orange band right here, we've visited the sky more than 100 times or 200 times, which nobody else has done quite like that. All right. So what can you do when you go visit the sky? You quickly discover that the sky is not stationary, all right? And if you have appropriate software to remove all the noise, and you can see our CCDs, our cameras were cheaply built, and so they're not performing that well. But if you have good noise reduction algorithms, all right, you can clean stuff up. And I don't know if you can see this, but there's a spot here, and every 2 hours you take another picture, and the spot moves across. This turns out to be a Kuiper Belt object, a big asteroid moving slowly on the outer fringe of the solar system. This same camera installed at Palomar found an object that was quite massive, in fact more massive than Pluto, and it caused the demotion of Pluto to be a minor planet, if you've heard about that. This was only possible by scanning the whole sky and looking for things moving across there. All right? The other stuff is, of course, you can find things that go bump in the night. Here's one of these supernovas. It's a star inside a galaxy, and here's the galaxy flattened out, and then if you look very carefully here, you probably can't see it. There's a bright spot that brightened. So this star is actually outshining the entire galaxy, which contains 100 billion stars. So that tells you it's a special phenomenon. What you can do is you can subtract off the light before the supernova appeared from the galaxy plus the supernova, and you see something called a point source consistent with one super bright star, right? And you can measure that luminosity. You can plot the luminosity, the brightness as a function of time, and it looks like this. And after you collect enough of these objects, you see that there's a pattern associated with them, and there are some systematic effects. The shape looks slightly different. You can correct for it. After you've done that, you can turn this supernova event into something that astronomers really love called a standard candle, where you know the brightness, and knowing that if I take the apparent brightness And I know the real brightness I can use, the brightness goes as 1 over distance squared that you learned in high school. I can get the distance of the object. And using this, people have proven, not our data is part of it, but have proven that the universe is flying apart as if there's anti-gravity, dark energy pushing it apart. Okay? And you can also do other fun things like this. This is a particular pretty bright star. And when you look at it and you plot luminosity as a function of time, you get a point here. You do it the next night, the point's way up here. You go down, you've got a complete scatter plot. Say, what the heck this is going on? This star is crazy. It's stochastic, right? But if you're clever and you mix around, you discover, hey, what if I take all the points separated by 1.5 hours, and you discover, hey, they're all the same brightness, okay? So this is a periodic blinking star with a frequency of several hours. And if you take the luminosity and it's called phase folding as a function of the period, like every 1.5 hours you plot those points, you get a beautiful diagram. This is not random at all, okay? So how do you find this, okay? Well, what you can do is you can take intensity as a function of time, and it's kind of a mess because this telescope you see has data gaps. There were clouds, stuff broke in the telescope. There are points that are off. This is very noisy, bad data, which causes all sorts of problems for standard applied mathematics stuff. Okay, but if you just go ahead and blindly Fourier transform it, you'll see that some strong periods pop out. If you do a modified version, this is a different statistic, same thing happens. And then if you fold this and just require that the points do not scatter randomly and you have a measure like how close are the points clustered, you pick out the same period and that's what you get. All right? In order to do this though, I have to go searching in order to catch this, produce this curve. For every object, every light curve, I have to search through 200,000 periods. Okay? And do some other cleaning stuff. So there's actually a non-trivial amount of computation in doing that. And how many objects there are in the sky? Well, it depends what you want to search. But for this telescope and its size, there are up to like 500 million objects that you could search. So if you want to make a complete all-sky survey of these, there's a non-trivial amount of big data, pattern recognition, data cleaning, and stuff that needs to go into it. All right. So just to give you a feel for what we're dealing with this particular project, how much data are we talking about here? If you consider what you can do from the ground, we've reached an interesting point in time. Because stars twinkle, unless you do something special, you can't do better than 1 arcsecond of resolution, whatever. And that means that there's no point in building higher pixel detectors, except unless you want to somehow sample the resolution better. But to 0th order, okay, this is the best you can do until you play tricks and go into space. And in 1 square degree box, I had the moon inside it. Therefore, I'll end up having 4,000 by 4,000 pixels, which is twice the resolution of an ultra-high definition TV frame, all right? And there are 40,000 degrees in the sky, and if you interpret how many frames is that, okay, that would correspond to about 6 hours of uncompressed progressive ultra-high definition video at 60 frames per second. So it's actually not that large amount of data anymore. This was unthinkable when I was in graduate school, but as often happens, this was also unthinkable. My thesis was partly done on a computer, one of the best supercomputers at Cray 2, with 2 gigabytes of memory, which is unheard of. This thing has 2 gigabytes of memory, okay? So, and then if you put in standard color information, you end up with, okay, made a mistake, 2 times 10 to the 12 bytes or 2 terabytes, okay? You can hold the entire sky as detectable by human eyes with reasonable telescopes in a few terabytes, okay? And therefore, you might think astronomy is over, all right? Let me assure you there's lots of things we can do to add another factor of 1,000 to this. Okay, for example, your eye measures 3 colors, red, green, and blue, right? But if you take the light that's arriving you and to disperse it as a function of energy or frequency, you'll see all these spectral lines. It's called a spectrum, atomic spectrum. So instead of having 3 colors, you'd actually like to have 4,000 measurements as a function of intensity. And then it turns out that objects don't emit in the optical. Most of the radiation comes somewhere else. You want to add a few other decades of energy resolution. And so I can blow up this number. But this has been a holy grail for many years. Let me make a whole picture of the sky. All right? That's what it takes to do it for astronomers for the last 100 years. That's what they expect. And then the next step is the sky is changing. So let's do it again. And in Quest, we have like 100 exposures, a third of the sky. So we're dealing with hundreds of terabytes of data. So that's what we need to deal with. Okay. And are there any special data needs besides the ability, the need to crunch this rapidly? Okay. this data, unlike other kinds of data, like last year we had maybe a talk by geneticists, the gene sequencing machines are getting faster and faster every year. So if you lose all your data, well, that's not such a big problem as long as you're not sampling a very esoteric population. You just bring in a few hundred volunteers, and the machines now are 10 times faster than a year ago, and you quickly regenerate your data set. Here, that's not good, because you may know, like, there was a crab pulsar, a neutron star that was produced as a result of a supernova explosion, and people went back to Chinese records in 1066 to identify this guest star that appeared. Okay? The universe is changing all the time, and what it looked like in the past is extremely important for interpreting what happened now. So it has deep archival value. This is why people have not thrown away these photographic plates. There are a bunch at Yale. Harvard, when like 2 years, we'll have ended up digitizing like 20,000 of them, and they'll be converted into a more usable format. Okay? But we want to make sure this data propagates in time and is properly curated. So that's one of the key things. All right. So that's that aspect of it. And how's it being handled? All right. So to show you why we're a pain in the neck to ITS and stuff, it's okay. The data is currently handled by high-energy physics nodes on Omega, and maybe about 40 terabytes of disk space. We have 25 terabytes on the RSS server. And then we have a mirror and comparable computing power at Berkeley at the National NERSC DOE Supercomputing Center. But right now, to be honest, the bulk of the analysis that finds these R-Lyrae stars and everything is done by 2.5 4U boxes, white boxes, with 12 Intel cores each and 24 disk space filled with 3 terabyte commodity drives from Newegg, if you know what that is. And it has what used to be, not anymore, a large amount of solid-state drives, which allow you to move data quickly, and a large amount of RAM. Used to use a lot of RAM, fast RAID cards. It's a specialized architecture to move data fast. It's putting a lot of data next to CPUs. So one of the themes that is emerging in our field, a lot of other fields, I think, is having an architecture where data and CPUs are next to each other, because moving data is extremely expensive. So you want to do the computation as close to the data as possible. So this is doing it, and we're running a mix of operating systems. The bottom line, though, is depending on what you're doing, choose the best tool for the task. These 2 boxes cost $10,000, and for certain benchmarks, they outperform Omega hardware it costs at like the $500,000 level. So there's a big performance difference. Imagine what you could do if you had 100 of these boxes, and we tried to put an MRI proposal. We didn't get it, but something did get it, and this isn't so different from what we proposed. At Johns Hopkins University, there's something called the Datascope. It's like 100 machines like I just talked about, and storing the data local to the computer. Okay, one-to-one mapping of users to nodes to let them run their custom programs, and they add GPUs, okay, and get rid of various bottlenecks. So this is optimized to handle like astronomy-type data where lots of things come in. You have lots of little subunits, files that need to get moved around, okay? The old file system on the Omega supercomputer here was optimized for taking terabytes of data and streaming it sequentially and throwing it onto the hard disk as fast as you could. The kind of analysis we do has millions of little files that need to get gone through and cross-correlated and put together. So it's a different kind of architecture. But one reason, besides my great proposal skills, why this probably didn't work is Johns Hopkins has a great track record in this kind of area. There's something called the Sloan Digital Sky Survey, which is a full, really big map before Quest was made of the sky. And it involved millions of dollars and tens of hundreds of postdocs. And Johns Hopkins was one of the leaders there. So they have a track record. Yale in astronomy does not have that same track record. And I think in other fields, we don't quite have it either. So I'm hoping by bringing people here together that we can all get together. We have the knowledge, because I know we've got people spread all over, and enhance our ability to do stuff like this. Okay. Is there a next generation? Where are things going? It's only going to get worse. Okay. There was this picture of a Schmidt telescope. Okay. And the person standing next to it was like this large. Now the person is this large, and you take a big mirror telescope you've seen and you squash it down. You make it a very fast lens so it can see a large amount of sky all at once, and you increase the mirror size by a factor of 10-ish. Okay? This is the biggest, baddest, okay, widest, fastest, deepest eye of the new digital age. All right? This thing is going to be producing data. It's called the Large Synoptic Survey Telescope. Synoptic means daily. It surveys the sky every day, basically. And what's the data scale for this? The numbers, the resolution is not that different from before. They want to sample the profile of the light. So they have, instead of 1 point per pixel, they have 5 or 10, all right? They can do half the sky every night. So they generate 4 petabytes a year, right? And that amazed me and other astronomers until you start Googling around and look at the data sizes of data sets like eBay and stuff. they're also in the petabytes. So one thing that's changed with astronomy is we've been a little spoiled in thinking we're one of the biggest, baddest data generators in the town. We're not. The industry web is far outpacing us. And anybody who has large sensor networks, they're generating huge time series just like we did. And you eventually will have thousands of sensors. Or imagine you're predicting traffic patterns. Google does this to make your Google map. You track 100,000 cell phones and how their velocities go, and you can find traffic drop. That's a huge data set. That's even worse than what astronomers are doing. So we're not necessarily the biggest, baddest guy in the town. In fact, my feeling from looking over this was, help. A lot of stuff is going on. Technology is evolving very fast, and I need to get up to speed. And even though I've only been here 20 years, a long time, I'm not that old, but I was not trained in any of this. All right? And in our department, I would say mostly the postdocs we hired recently know some of this stuff. The graduate students coming in don't. So somehow we have to change how we teach, acquire the technology, train the new generation of grad students, maybe some of which will have a specialization involving computing data aspects. So not only do you have to, this thing generates some interesting science cases because when the supernova goes off, you have to jump on it with many instruments, and we're not ready for that. But you better know something about data cleaning, which is before you do the data mining, and there's an article in the New York Times that said 80% of data miners spend their time cleaning, so they're better known as data janitors, okay? And how to pull signals out of messy data. And then you're not going to deal with the full data set, but I wouldn't be surprised if you took some subset of it, like 10%, 5%, 1%. We're going to be pulling in hundreds of terabytes over the network, and we need to push it around with ease. That's not quite possible today. So we need to evolve as a university, I think, to be able to do this, because other fields are in the same boat. And that's pretty much what I wanted to say. General comment about where astronomy is going and where the emphasis was needed. At various times, people have said, no, we need the biggest, baddest computers. And other times, people said, no, think before you compute. And what's actually happened is, since I graduated from graduate school, our ability, for example, to simulate the universe from the first perturbations that made the microwave background then collapse to make the galaxies we see today, that ability has improved by a factor of 1,000,000 in 20 years. Okay? Half of that in log space, a factor of 1,000, came from the hardware. The other half came from novel algorithms and ways of thinking about the problem. So the people and the knowledge about the problem and the physics and the hardware are both equally important. And to make best progress, you need to push on both fronts. And one way to do that is because astronomers are not necessarily the forefront. It's for all of us to get together and talk. So a proposal might be some of us could meet semi-regularly and talk about what are you doing that's cool in your department, and hey, maybe I can do the same thing too. So that's where I'll leave it at. So astronomers generate and use lots of data, and we need to learn how to move into the really big data era ourselves. And some of the tools that you can use are not available off the shelf. We have to develop our own. Okay, thank you.
So all three members of the panel are available to take questions. I think we've got about 10 minutes. So please.
Hi, about astronomy. I guess all the photo pictures are optical, right? So how the weather would affect on that, and how much you would have to discuss what would be the cutoff for the pictures are not would be usable.
Right, exactly. That's the name of the game. And so if you require the pristine conditions, depending where you are, if you're in New Haven, none of the nights are usable. Where this telescope is mounted in the middle of the desert in Chile at very high altitude, where there are very few clouds, even then 10% of the nights are lost. But some of them you can recover because even though there's a cloud, the distortion is not so bad from the wind. The cloud absorbs a lot of light, so the stars are dimmer than they ought to be. But if you have enough area on the sky, you can see, hey, all the stars are dimmer, and you can compare in the past. And you can actually correct that out. So there's some real-time corrections you can apply that enhance your probability of success. But as you saw in those gaps, we were losing 5 or 10% of objects. And some people take the attitude, I only want clean data. But if you do that, you lose, you lose some of the time series. Like you're looking for periodic objects, and you throw away all the bad data with some criterion, you will lose detection power. So what people tend to do is you specify how much data do I throw out, and you assign a quality criterion, and then you adjust that. But one of the tricks is to figure out how was the weather. And so astronomers now have weather classification systems or auxiliary telescopes like this LSST, while other telescopes whose sole job is to figure out what's happening with the weather and the transmissivity of the atmosphere and everything. So that's a crucial point. And one way to get around that is to put your telescope in space and forget about it. So there'll be a next generation space telescope, for example. But that's what makes our life so difficult, is we'd like to have a nice continuous data train that's evenly sampled, and you apply your Fourier theorem. Well, no, you lost data for 3 hours, and this data, the error bars are twice as large. And so you need a system for doing knowledge inference based on fuzzy, messy, yucky data. So that's the future for us.
Just a quick note to the panel speakers. As you are answering questions, please come up to the podium to answer the questions. Thank you.
Sorry.
For the astrophysics, I know there's ideally the data would be safe, raw in archive form. But are there efforts to? Because I would think that over a long period of time, the changes in all of these images would be just slight. And is there an effort to like compress the data over like the past?
Yeah, you can absolutely do that sort of like video compression in the same way. The problem is though that the range of astronomical timescales is large. I can show you like one of these blazars, the black hole. Its luminosity changes by more than the luminosity of a galaxy in 5 minutes. It's a trick involving relativity, but it's doing crazy stuff on 5-minute timescales. Okay, and other things take years or 100 days. So coming up with a suitable time frame depends on the science that you're doing. The people in this LSST project are doing exactly what you're saying, but they're having big debates. All right, how are we going to compress it, and what are we going to analyze it by? And different scientists want to have different algorithms. So the best thing is if somewhere in a vault somewhere you still have the data, when someone comes up with a clever idea, you can find it. Another thing that compresses data is if you look at our data and make a picture, most of the sky, 95% is filled with noise. All right? But unfortunately, if you know where an object is and you have 100 exposures and you add them together, what was previously noise, the signal will actually pop out. And so if someone else later discovers an object and you threw the information away because you compressed it because I didn't find anything there, you've lost some discovery potential. Of course, there are funding and space constraints and everything, so you do what you can. Ideally, though, every single pixel has information. It's for people down the road who have different ways of analyzing it and different thoughts. And, oh, that was a really interesting phenomenon. What? You threw away all that data. So, and the human eye doesn't care about things with frequencies much faster than 20 per second and stuff. So we can throw away a lot of data in JPEG stuff that you can help with. You can do some compression. There are lossless compression algorithms. You can gain factors 2 or 4, and people will use those. And we use that. We have a gain of factor of 2 by compression, but not factors of 10 or 50 like in video compression. So that's a huge topic for and something to be discussed.
Hello. Okay, it's on. First of all, that's messed up about Pluto. I think we can all agree on that. My question is, I have a quick question for you and also a question for the linguist. First of all, do you have an explanation for why the things that we observed, like the supernovas, were outliers in 2 different ways at the same time? One that we observed them, and the other that they looked nothing like the ones you then later saw? And I'd love to hear that explanation. And my question for the linguist is, as I understand it, and I was in the bathroom, so I might have missed the part of the talk where you talked about your data. Is this like a snapshot of the current state of languages? And to what extent, I mean, obviously languages evolve over time. That's why we have a genealogy of languages. But what is the time frame where you could actually see that happening? Because that's like one of the most fascinating questions for me about language. Thank you.
Yep. In our case, it turns out, for example, if you look at the sun, and that's the first star you ever saw, it turns out to be completely average. Okay, but when you have, it's just small number statistics. There's some chance always that you'll find a guy. And to be honest, yeah, most objects are not such large outliers. But if they were rare and you take the first one that shows up, oftentimes it's not representative. Like if you're admitting students, you want to talk to several people. Never do, unless you absolutely have to, don't trust what the very first person tells you. And if you have to bet, okay, you'll bet that he's an average person, but there's always outliers.
Just regarding the situation with language documentation and the language data we have, in some places, we're really lucky to have historical documentation. So for the European languages, we have records that go back quite a while. For Australia and many parts of the world, it's very like many parts of the world, where all we have are the things that were attested in this century. And many of these languages are not spoken anymore. So we have a snapshot of what these languages looked like, perhaps in the early 20th century, perhaps later in the 20th century. But that's what we're looking at, is one snapshot in time. And what we as linguists are trying to do, especially we historical linguists, is trying to leverage that data to figure out what the data tells us about the past. So those phylogenies you were talking about, those have actually been constructed from data about attested languages, not about historical languages, for most parts of the world, where we're actually able to use the contemporary data to reconstruct the past. So we've got a window of about 10,000 years, most people think, for that. Yeah.
So about language, I mean, have you looked at the relation between emotion and the actual acoustic signature of the words? Because this might become common across languages quite a bit.
There is work on that. It's called corporeal sound symbolism in the sort of Hinton et al. Schema of sound symbolism. So there's definitely work on how acoustic frequencies signify things about emotion and state of mind and things like fear and anger. Yeah. We don't have data about that for these Australian languages. We don't have any. If you have a corpus of actual conversations, you might be able to extract information about that, but we have limited data.
So in order to keep us on schedule, let's take a few moments and thank the panel, and then maybe 5 minutes to get set up for the next speaker. Thank you.